have data coming in one at a time.
It's not focused clearly for some reason. I guess we should start publishing the slides separately from the talk.
Do you have like a public thing?
Sure.
Well, our presenter today is Dr. Preethi Jyothi, who's a Beckman Fellow, one of the postdoctoral fellows. She received her PhD from the Ohio State University, working on articulatory feature-based models for pronunciation models for automatic speech recognition. And that expertise in finite state transducers is being applied to a completely new area, which is schematized by this map. And so she's going to tell us more about Mismatched Crowdsourcing. Thank you.
Thanks a lot. Thanks to everyone for coming to the talk. So today I'll be speaking about acquiring speech transcription using mismatched crowdsourcing. I'll explain a little about what these terms mean. This is joint work with Mark. So this is a map of all the major language families in the world. So this is from artisia.com. It's adapted from Good's World Atlas. And so there are a little over 6,900 languages in the world. But a very small fraction of the world's languages have supporting speech and language technologies. And it's a fair number to say that less than 30 of these 6,900 languages are considered to be well-resourced or high-resource for automatic speech recognition applications. And so there's this distinction made between high-resource languages or well-resourced languages and low-resource or under-resourced languages. And by low-resource, we mean the lack of electronic resources which are needed to enable speech technologies for a new language. So for example, transcribed speech data, pronunciation dictionaries, vocabulary lists, and so on. So these are not readily available for a very, very large subset of the world's languages. So a very natural question to ask is, why do we care about building speech recognition systems for all the languages of the world that are possible at all? And so, of course, the first and foremost reason is that speech is the primary means of human communication. It's fast, it's comfortable, it's easy, there's no practice required. And it's also modality independent, so it keeps your hands and eyes free to do other things, so you can combine it with other modalities. Another point to mention is there's rapid growth of telephony-based services in developing countries, and so there's tremendous potential for ASR applications. And the last point, which I think is a noteworthy point, is that speech interfaces can be particularly useful for people who can't read or write. So if there were interfaces that work really well, this would potentially be really useful for this demographic. Okay, so what is the bottleneck? So the major bottleneck for building an automatic speech recognition system in a new language, just like for any other supervised learning problem, is getting large amounts of label data. So here, label data, we mean transcribed speech data, so speech with corresponding transcriptions. So to derive this, we need access to native speakers of the language that we're trying to build a system for. So crowdsourcing has been recently explored as a viable technique in order to derive speech transcriptions for large speech databases. And the most notable work is by Novotny and Cannissen-Berg in 2010. So for people who are not familiar with crowdsourcing is basically purchasing data from very large online communities. So you can post individual tasks which are really simple for people to do, and people do these tasks in large online communities in exchange for some payment. A very reasonable amount of payment, which is debatable on a different topic, which I'm not going to get into now. But so this is one viable technique that has been explored in recent work, but it's probably not always a viable solution. So here are two kind of instances where this is not a viable solution. So if you're trying to build an ASR system for, say, a minority language, so for example, Polynesian languages like Maori and Samoan, they have far less than 1 million native speakers. So this is probably not a viable option. And nor if the native speakers, there are plenty of native speakers, but they're not easily accessible online. So Pavlik et al. Had a study where they do a language demographic study of a huge crowdsourcing platform called Mechanical Turk. And these are examples of languages, so Swahili and Punjabi, are languages which have millions of native speakers, but they are not very representative you don't have many native speakers easily accessible online. So a question that was particularly interesting to us was, in the event of not having native speakers of a particular language, can we use crowd workers to transcribe a language which they are unfamiliar with? So on the face of it, it sounds like it's almost an impossible task, but this is essentially the problem that we are studying more. And the term that we coined for this is mismatched crowdsourcing. Please feel free to interrupt me if you have any questions. Okay, so in a lighter vein, just this act of listening to a foreign language which you don't understand can be very amusing at times. So there's a quaint story of how this term came about. So the term mondegreen refers to mishearing phrases such that it gets a different meaning. So this was coined by Sylvia Wright in a 1954 article, and she used to listen to a folk song, and the lyrics went something like, and they had slain the Earl of Moray and laid him on the green. And she always misheard it as Lady Mondegreen, and that's how Mondegreen came about. And so there are also cross-linguistic mondegreens. So the Japanese term for interpreting lyrics in one language as similar sounding lyrics in another language is soramimi. And these are really popular on the internet. And so I have a short clip of a German song which is misinterpreted in English. My apologies to anyone who understands German in the audience. But so we just take a look at.
German is that the lyrics written in English are too plausible.
Exactly, yeah, it definitely seems plausible to me, but if someone understands German, I think it probably wouldn't match at all with the original lyrics. Okay, so, but jokes aside, so there's very interesting scientific questions. If you try to understand how does one perceive a foreign language, so how does one mishear a foreign language? And there's a lot of relevant work in second language learning and second language acquisition in the linguistics literature. But we are going to approach this problem slightly differently. And so there are two main questions that we're interested in. How noisy is this cross-linguistic perception? And I'll come to what I mean by noisy. So are there systematic patterns of errors that we can exploit? And also, can we quantify how much information is lost in such a mismatched transmission? So we essentially represent this entire problem as a noisy channel model. So the input is text in the foreign language, so that's denoted by X, that is encoded into speech by a native speaker in that language, so it's denoted by A. And this is fed as input to what we call a crowd channel. And the crowd channel produces an English corresponding transcription, which is denoted by Y. So a single invocation of the channel would correspond to an individual crowd worker who listens to a speech segment and writes down an English transcription which most closely matches what they heard in the new foreign language. And now Y is fed to a decoder, and the decoder is considered to be successful if it produces an X tilde which is the same as X, so you're able to recover the original text in the foreign language. So unfortunately, this channel model is extremely noisy. So irrespective of what the decoding algorithm is, there's too much information lost. So there's no way you can recover X from Y with just using a single invocation of the channel. And so we try to get around this by using a simple repetition code. And so here, this means you have K independent invocations of the channel, one for each repetition of the speech segment. And now these are fed to the decoder, and yeah, so this is essentially the setup. And so in this case, this would correspond to K different crowd workers listening to repetitions of the same speech segment. So given that this is our framework, there are two main components that need to be implemented. So first, of course, is what is the decoding algorithm, what is the decoding rule. So we use a very simple maximum likelihood decoding rule. And so for this, we need to estimate the likelihood. And so that is our channel model. And so we make an assumption that this kind of cross-linguistic misperception has finite memory, and so we can use a finite state transducer to represent the channel, to encode the channel model. So the channel model is trained by training instances x and y, where x corresponds to a phonetic representation of the text in the foreign language that you're trying to recognize, and y corresponds to English strings, which is what you get from the crowd workers, corresponding to what they heard. So in this particular finite state machine, the transitions have input labels on each of the arcs, which correspond to phones in the foreign language. And there are also corresponding English letters, which appear as the output labels. So if you transition through the arcs in this machine, a sequence of Hindi phones would be mapped to a sequence of English letters with a particular path cost. And the costs we learn by using the EM algorithm to maximize the likelihood of the observed data. Again, please feel free to stop me if you have any questions. So this is a fairly standard model, and these kinds of models are very popular in transliteration. So here's an example of the kind of task that we set up. So the foreign language that we used was Hindi, which is most widely spoken in the Indian subcontinent. And so we took small segments of Hindi speech, and here they correspond to isolated words. So if you listen to this clip, so just out of curiosity, what does that sound like to people who don't know Hindi in the crowd, I guess?
Hula?
Okay, yeah, okay. That's much better than some of the responses we got. So there are multiple segments of speech like this, which were played to multiple crowd workers. So here are some of the responses we got from 11 different crowd workers. So you can see that there's a lot of variance in the transcripts in terms of how they heard this particular utterance of Hindi. So the next column corresponds to the decoding results if we individually decoded using each of these Turco transcripts. So you can see that Pura just appears as the best possible word in two of these, two instances, and it competes with two other hypotheses, which is pada and voting. And if you're wondering why voting, which is an English word, appears in this list, it's because lots of English words are used in Hindi, while speaking Hindi. And so this happened to be part of the vocabulary that we used. And the next column corresponds to...
How do you pronounce voting?
Voting, just like, I mean, the intonation might be different if you're speaking. Yeah.
Did you, so the original, the input signal, it sounds like it was lifted out of a context?
Yeah,
right, was it?
Yes,
yeah.
It was spliced out of
right.
continuous speech. Yeah.
So I think that's what's giving rise to these final consonants, because you hear, you can hear the articulation with whatever's coming next. It's
right.
P or K, I think.
Right.
You hear that,
yeah.
right? So,
Absolutely, yeah.
So I don't know if it would be fair to count that as a true error, and because it might not be actually.
That's true. Yeah, I think if we had not spliced out these individual sentences and actually given them instances of words spoken out with sufficient amount of pauses surrounding it, I think we would do even better.
Right, I think so. Yeah.
But yeah, this was the setup. And so here we see if you cumulatively decode using the first I interpret transcripts, then once you see sufficiently large number of transcripts, you start recovering the actual word. So a very quick overview of the experimental setup. We extracted 1 hour of speech from radio podcasts, which are available online from SBS Australia, which is a very large public broadcasting radio and TV network. And the vocabulary size for our task was around 2,500 words, so this is like a medium-sized task. And the task itself was to recover isolated Hindi words. So these are not phrases, or this is not continuous speech. So recover isolated Hindi words just by using these mismatched transcripts. And we used Amazon's Mechanical Turk, which is a very popular crowdsourcing platform. We had a total of 134 Turkers, that's the name given to the crowd workers, both in training and evaluation. We also asked them to give us a little information about their language background. So 73 of them knew only English, but there were others who also spoke Spanish, French. These were the most popular languages after English. Okay, so if we look at the error rates, so we're plotting the error rate, that is how often is the correct word predicted by our model, and we plot it against the number of Turkers. You see that if you only had transcripts from a single Turker, the error rate is greater than 50%, and it significantly drops as you increase the number of Turkers. And you see similar trends when you plot like the 2 best and 4 best error rates as well. And you can also see that there is a trend of diminishing returns. So the drop is higher with the first few additional Turkers, and then it kind of plateaus out. So there are 2 other questions that are very interesting to us. So one is, how does this mismatched channel look? What are the channel characteristics? And also, can we quantify how much information is lost in this channel? So to visualize the channel characteristics, we use the learned channel model to align Hindi phones with English letters. So on the x-axis, we have the most frequently occurring Hindi phones in our training data. And the y-axis corresponds to a distribution over English letters or pairs of English letters for each Hindi phone. And the colors in the bars just indicate how often this particular English letter or pair of letters was used for a particular phone. So there are a lot of interesting patterns in this graph, and we see some systematic mismatch patterns. So for example, the per phone in Hindi is written mostly as P or also B in English. The th, which is an unvoiced dental stop in Hindi, the th, and it's not a sound which appears in English typically. So this is written as either T or D, which is again a mismatch that we expect. And we also see significant deletion probability. So all the white space above the columns corresponds to when phones appear in context, there's a lot of the phones are lost. They're not perceived by the Turkers. But it seems like from what we are perceiving, there are some fairly systematic patterns that we can exploit. And the next question is, how do we quantify the amount of information lost in this kind of a channel? So we use an information theoretic quantity called conditional entropy, which is denoted by h of x given y. And there's a fairly standard upper bound that can be empirically estimated for h of x given y using cross entropy. But we observe that when we actually plot this bound, which is obtained using cross entropy, the bound degrades as you increase the number of Turkers. And this tends to happen because the errors in the channel model, they get amplified as you increase the number of Turkers. And what tends to happen is that you overestimate the entropy of infrequent events. And so what we do is that we treat the infrequent events separately and estimate the entropy of these infrequent events in such a manner. And so then we get a much tighter upper bound, which we call gated cross entropy. So for people interested about how exactly this bound was derived, we used an auxiliary random variable W. So W is either epsilon when Z, which is a binary random variable, is 0, or W is X when Z is 1. And how do you set this binary variable Z? Z is set depending on how confident the channel model is about a particular Hindi transcript given the mismatched transcripts. So intuitively, this auxiliary random variable W represents side channel information. So it indicates when is the model not good enough and when does it need to be corrected. So if we use a standard inequality, which holds for all x, y, and w, we get this particular form. And if you expand the terms out, this is the final bound that we get. So this first term corresponds to the case when this binary variable Z is 0. And so this is upper bounded using standard cross entropy. And Z is 1 when the channel model is very uncertain about what the Hindi transcript is corresponding to the mismatched transcript. And so by optimizing for Z, we can actually make this bound much tighter. So this is kind of the first part. So we have a framework where we can use this to acquire speech transcriptions using mismatched crowds. And on a medium-sized isolated word recovery task, we are already obtaining greater than 85% accuracy by using 15 repetitions. So the next question, which is is interesting to us is how can we extend this to continuous speech recovery?
One question about your 2,500 words. A section of all the different kinds of words by part of speech or by length or by frequency or.
So we didn't explicitly control for part of speech or so these were just all the words which appeared in the one arm of speech that we extracted, which was just from
from different speakers. Or
this was 7 different speakers. And yeah, they just
function words are in there too, and
yes, there are function words
and errors. Did you take out these?
Yes, I explicitly proved out the errors. Yeah, so there are no errors in the library, but there are function words. There are words of varying lengths and different parts of speech. Yeah, so we didn't explicitly control for.
And did you control for like laughing or copying or non-speech noises?
Yes, absolutely.
And those are gone?
Yes.
Yeah.
Yeah. Okay, so I can move on to the second part.
That's great, that over 85%.
Yeah, that was pretty encouraging, I think. That's what...
It's actually better than Kallenberg reported for native language crowdsourcing,
yeah.
or at least a single crowdsourcer.
Yeah. Of course, it is an isolated word task, so it's definitely much more constrained, but still...
it makes it harder in a way if there's no language model.
That's true. Yeah,
well, if you don't know the language, then there's no language.
That's true, yeah. So actually, yeah, isolated word tasks, I think this is very comparable to like unsupervised approaches which are used to kind of recover isolated words. They get numbers which are very similar to this. I think it's slightly worse.
I have a question. So Hindi is a phonetic language. So,
yes, so there's
when you're going from the word to the English spelling, I would think it would be a slightly easier task.
Yeah.
Suppose you had to do the opposite, say, so you have to go from English to another language, where English, the way you say the word is not how you write it. Would it be a lot more difficult?
So the idea is that the channel model should capture that variation. So if you have enough data, the fact that the letter A in English stands for all these various different sounds.
Enough, or
Yeah.
So it actually would be worse going from Hindi to English, as you have, than going from English to Hindi. That's a piece of cake.
Yeah.
That's
well,
easy.
No, the other way.
But then
recovering the English, you would need to have an English dictionary that actually told you what phones are produced in each word. And
but rendering English
if you have that, then it would be easy, and if you don't have that, it would be impossible, I think.
Yeah. But rendering the English sounds in the text of a language where the spelling is phonemic is very straightforward. But rendering any sounds in a text where the spelling is not phonemic is, I mean, you could see that in your responses if people were spelling using spelling conventions.
Yeah.
Oh, that's what you're saying. Okay.
English DTD, like decomposing.
Oh, I have no.
English, so okay, maybe my question was English to English then.
Yeah.
Right, but yeah.
Or how do you transcribe?
There's a point related to your interpretation of what you said that we Preethi has actually experimented with taking this finite state transducer and decomposing it into a phone-to-phone mapping, which just represents the second language perception, and then an English perceived phone to English letter mapping, which is basically the represents the orthographic variability in English.
And that actually didn't that performed worse. Oh. And it's probably because there's a lot of non-determinism in the English letter to phone.
I see.
And so that actually ended up hurting the accuracy.
So what was the second task, you said? English?
Oh, so it's the same, so it's just a different model. So here we're learning mappings from the Hindi phones directly to the English letters.
Right.
So instead of that, break this up into 2 machines, one which learns a mapping from English phones to Hindi phones. So Hindi phones to English phones, and then a dictionary which goes from
English phones to English.
English
So that's
text.
where there's
So
a
that's
lot.
where there's a lot of
yeah.
that kind of thing that you talked about. Yeah.
So just out of curiosity, what about the other languages? Are they phonetic? Like Swahili, the ones that you said were...
So Swahili has a high degree of correspondence between the orthography and the sounds. There are lots of languages where it doesn't. That's not the case at all.
What about Punjabi? I don't know.
Sorry?
Okay. What about Punjabi? I'm not sure.
Punjabi it's quite similar to Hindi. I think I don't know.
I don't know Punjabi very well.
Okay.
Yeah, I believe so.
So Punjabi is pretty. So there is a
Why would it
tonal
matter?
component to
Sorry.
Punjabi. So Punjabi does have tones, but other than that.
Actually, I'm sorry. I guess my question makes no sense. It would make sense if you were transcribing from Hindi to Hindi. Otherwise, it doesn't make much sense. Sorry, maybe it was
No.
not enough.
No, I think it was a relevant question. So.
Yeah.
Yeah, there's not
Maybe
always
that-
a high degree of correspondence between spelling and sounds, and how do you
Right.
counter that? Yeah.
So it's really, there's really two problems you're trying to tackle at the same time. One is, how do you hear the sounds in a language you're not familiar with? And then, how do you represent sounds in a language you're not familiar with, in your writing convention?
Yeah.
And those are two really hard problems.
Right. Yeah.
Yeah.
Separately.
Yeah.
Absolutely.
Yeah, I'm actually right now working on trying to take for all of these 70 languages, trying to create pronouncing dictionaries, and actually most of them do seem to be easier than English.
Oh, really? Oh, that's the
which is a
relief,
big,
actually.
yeah, a relief. I mean, of course, Japanese, Korean, and Chinese are not, but
Yeah.
other than that, most I mean, all the Brahmin,
Okay.
all the languages that use Brahminic alphabets
Right.
are considerably more phonemic than English is, I think.
Right.
And languages like Swahili that have been invented within the past 1,000 years
Yeah.
even more regularly as well.
Right. Yeah, and there's an additional dimension, I mean, of variability, which is we don't really control for the language backgrounds of the talkers. Their spellings also can be very, very variable. So for someone, for a French native speaker, for example, they'll use a different spelling to represent the same sounds, which as opposed to an English native speaker. So.
So when you have diversity in your crowd, do you
Yeah.
think that decomposition of phone to phone and then phone to grapheme is more effective in that setting?
So I actually think that that decomposition is not effective when you have all this diversity in the crowd workers, because that decomposition is assuming that you're going to use the English style of.
What if you can condition on the linguistic background of the
Yeah,
worker?
yeah,
I guess
yeah.
is the
So you can
question.
condition on the linguistic background,
Then
which
you
we
need a
need
lot
to
more.
collect a lot more data.
And the spelling
but,
ability.
Yeah. of course.
Yeah.
Oh, so maybe we should be hiring Turkers in France instead of the U.S. or in some other country,
Yeah.
in any other country in the world, any non-English speaking country.
That's true. I think if you get enough data and you're able to separate out the channels based on like language family or something like that, I think the models will be more like.
Were your Turkers restricted to U.S. IP
No.
addresses?
No.
So they were,
This was all-
but there weren't, because a lot of Turkers they have Indian IP addresses.
Oh, right. Sorry. Yes, they were restricted to the US. Yeah, they were restricted to the US. So the only condition was that they shouldn't know Hindi, and hopefully, I mean, the responses definitely seem to suggest that they did not know Hindi, but. So, how would we go about extending this to continuous speech recovery? So there are two main challenges with respect to continuous speech. So the first, of course, is now you have noisier transcripts because your utterances are longer, and so you have higher error rates in the transcripts themselves. And another main issue is efficiency or scalability. How do you scale this approach? So the exact decoding time can be represented in terms of these two different approaches. So the min of these two approaches. So if T is the size of the decoding graph for a single transcript, you can imagine building a single decoding graph of size T raised to n, where n is the number of transcripts, and then you do exact decoding. But this is not viable at all for n greater than 2. In the standard ASR paradigm, n is 1. So T is very large graph in itself.
What do you mean by decoding graph?
Oh, so the decoding graph is the composition of multiple finite state machines. So it's essentially a search graph.
Yes.
So you're starting with phones, and then you eventually want to recognize words. So you have a pronunciation model, and then you have a language model, which gives probabilities over word sequences. And then you compose all of these machines together, and so you have this large search space. And that's all the decoding
What's the
graph
size
is.
of T that you're using?
Yeah, so T, the size is, it's close to 1 million arcs. So it's a machine which has close to 1 million arcs, and it has around like 300,000 states. So it's a pretty large machine. And the second approach is if U is your utterance space, then for every utterance in your utterance space, you can do n individual decodings with decoding graphs of size t, and then you sum over all the scores. And this is exactly what we did for the isolated word task. But this again is not feasible because now with continuous speech, the size of U is going to be exponential in the length of the utterance. And so we use an approximate decoding approach. And so we use two ideas to kind of efficiently do this approximate decoding. So one is, what if we could merge the transcripts into a single transcript and then do exact decoding? So we in our experiments, we don't exactly merge it to a single transcript. We produce a low entropy distribution over the transcripts. But for this talk, you can just assume that it's going to be a single merged transcript. And the second idea is basically you decode from a short list. So if your utterance space is really small, then you can do exact decoding using all of the n different transcripts. And so if you can generate a short list of hypotheses from different variants of these merged models, then you can do exact decoding just using this small hypothesis space. So I'll show some illustrations of how we go about merging transcripts. So this is a short phrase. So now we're no longer restricted to isolated words. So this is a short phrase in Hindi. It's kiya jayega. So here are some mismatched transcripts from the crowd workers. So the first step, we essentially align these transcripts. So this is just a greedy alignment of all of the transcripts, and we introduce deletion symbols whenever necessary. This was produced using a very popular toolkit in the ASR community called Rover. But here, immediately, a few kind of inconsistencies or discrepancies are apparent. So for instance, we would want K and G to be aligned with each other. We probably don't want G and E to be aligned with each other. And there are issues like this. So the CH corresponds to a single sound, ch, but the letter H gets aligned with Y, and that is something we would like to avoid as well. And so we do a few pre-processing routines. So one of them is we take these frequently occurring pairs of symbols and we create a new symbol for it. So capital C corresponds to CH, capital E corresponds to EE, and so on. So this could be done like more systematically by actually using a dictionary, which we just discussed. So use a dictionary in English to kind of extract these sounds and then look at the distribution of all the letters that possibly occur. And I tried doing that, and that actually again does worse because there's just too much. It's a very high entropy distribution. So we want there to be fewer choices. And the second pre-processing routine is we just kind of collate all the symbols into equivalence classes. So all the vowels are a single equivalence class, and all the consonants were again grouped into different equivalence classes depending on the place of articulation of the Hindi phones closest to the sound. And so this is the resulting alignment, and you see that this looks a little more meaningful than the alignment that we saw in the previous slide. So if we were to only look at the most frequently occurring symbol in each column, this is our merged transcript. And so if you look at the merged transcript and the actual Hindi transcript, there's quite a lot of resemblance. So if all the transcripts behave this well, we would be done. We would not need to do anything more. But that's rarely the case. And so an additional technique that we used, we call it contextual weighting. So the idea is, instead of just finding the most frequent symbol in each column, we actually assign what we call contextual weight to each symbol before aggregating the most frequent symbol. And what this contextual weight means is the contextual weight of a particular symbol in a transcript is actually a measure of how the neighboring symbols match with all the other transcripts. So I'll show you an illustration and hopefully it'll be a little clearer. So again, this is another phrase in Hindi, it's Abhiyan K. So let's assume that these are the winning symbols in each of the columns, except for the second column. So we need to find the winning symbol in the second column, and we know the winning symbols in all the other columns. And so these are the highlighted letters are all the corresponding winning symbols in all the other transcripts. So if we only look at the symbols appearing in the second column, we are essentially, well, the colors don't show up very well, but maybe, hopefully they kind of become darker, the highlighted ones. But essentially, the symbols the V symbols here are going to get votes from all the winning symbols in their corresponding rows. And the same goes for the B symbols. And so the V in the second column gets, the 3 V's get 12 votes from all the winning symbols, but the 2 B's get 14 votes from all the winning symbols. And that's because there was a lot more correspondence in those particular transcripts. And so now the winning symbol is actually B. Previously it would have just been V, because that is the most frequently occurring symbol, and B is more desirable.
So your assumption here is that because each line represents one person's, one Turker's response, right? So your assumption is that a Turker who does better on more phones is more likely to have the accurate answer for the phone in question.
Yes, and a Turker who matches with other Turkers on more phones is probably more reliable in some sense than.
Do you have to adjudicate between those two metrics? Like, are you overall more? Do you have overall more accuracy, or are you more likely to be accurate with other people?
So I think this is kind of this is leaning more towards the second part of it, which is how accurate are you? Because we don't have a notion of accuracy, but these are all different transcripts, and so so repeated orthography is our metric of we trust in your transcript more.
Well, so actually just now describing this so far, you said that suppose we know the correct answer in every other column.
Yeah.
And so what I think what you're saying now is that we don't actually know the correct answer in the other column. Those assumed correct answers come from majority voting in the other columns.
Exactly.
So it has to be sort of an iterative process where you find the correct answer by doing a majority vote, and then you do a re-estimation by using that majority vote to reweight each individual Turker.
Yes, absolutely. So the winning symbol was just for illustration purposes. There is no.
So what Jennifer was asking was if you assume that you do know the correct answer, then that would be great.
Then that would be great.
You would take whichever Turker had the correct answer in all the other columns, and that Turker would be most likely to be correct in the column you're looking at.
My actual thought that motivated my question was that I was imagining that you might have an individual who's just not very good at hearing the distinction, but they're really good at hearing all the vowels, and then you would, so it may not necessarily be the case that someone who's good at one kind of phone will be accurate at another from a different class, phone class.
I see,
So I was just wondering about that. I'm speaking from personal experience. No, I'm very good at hearing some phones in foreign languages, and I'm not very good at others. So.
Right.
And I suppose individuals have different strengths.
Yeah,
and I guess this was the premise of this idea of decomposition, right? The simpler questions, certain people would be better at certain things, and so on.
Yeah.
All right, that's true. Yeah.
And match with other people makes me nervous, because it's very common for people to just mishear. I mean, so English speakers are likely to consistently mishear some Hindi phones. So the majority phone for some particular target could be wrong, and yet you might have that one individual superior listener who's actually got it right. And they'll never, their vote will never count. I don't know how you would discover them.
That's right. So maybe the solution to that is to actually inject some information about what you know about the phones in the target language. So you know that there are some phones which are probably going to be misheard or misrecognized more often, and so there you're going to be more cautious about just sticking to the majority vote. So here we don't do that at all. So this is something that, you're absolutely right. So we don't kind of take into account whether certain sounds, they're always misrecognized, but if all of them misrecognized in the same way, then that's definitely not sure.
Although that's fine for you, right?
That's if that is. Yeah, I think consistency is.
I have a question.
Yes.
If you do that for different words, like some wrong rolling, so could it happen that they flip and never converge?
Yeah.
So you get V, so I changes to E, and then B changes to V, so I change E changes to I, and then
Yeah. So I think
that's possible, right?
That is possible. So so this is kind of a variant of like the power iteration method. And so,
Not just
but yeah,
thinking, so, because you must have stopped it at some point and you had a schedule.
right.
So how did you?
So actually, so this particular
Yes, sure.
but I did run variants of doing iteration till convergence. I never ran into a situation where it
And
didn't
practice
converge.
it never happens, but
In
I'm
practice,
sure we
yeah,
can
I'm sure it
come up with
could
an
happen
example with
theoretically.
5
Yeah.
words and 5 people. Or just
Yes,
flips
I agree.
over.
Yeah. Yeah,
That's
in
where it might be
practice,
really useful if you had some anchor sounds, some sounds where you have some independent reason to believe that people are going to be more accurate on that sound,
Mhm.
or in a certain context.
Right.
So the
Yeah.
vowel ah, for instance, quite
So vowels actually are quite
robust. I think.
yeah, but there are some vowels which are not robust as well.
Yeah, so ah would be really robust.
Ah is robust, but a and all is they're not robust. They're not the robust vowels. Yeah. Yeah, because there are no corresponding vowels in English to the a and all of Hindi. So the man. So it's not really a diphthong in Hindi. So it's similar, but yeah.
This is
Okay.
where some of Kathy Best's categorizations might be useful.
Yeah.
Are they the same phone but not quite the same phone, or are they really the same phone, or are they completely different phones?
Right. Yeah. Yes. That is.
Well, the other thing that occurs to me is that because the interpreters are writing down the letter sequences for what they hear, they're also presumably influenced by the bigram frequency of letter sequences in English, and would be more likely to transcribe letter sequences which are represented in English,
Yeah.
but which may not actually be the favorite letter sequences or phone sequences in the target language.
Yes. Yeah. So.
Do you think that's
Could-
really the case? Like, I would expect the opposite. Like, if I'm transcribing something I don't know, I would use weird combinations that don't occur in my native language.
No, actually, I think you'd be likely to write down the thing. You're trying to map this weird sound to something that's familiar, because you're told you have to use English letters to write. I mean, letters you associate with English sounds to write down what you hear. So I think you would be biased to write down sequences that are common. So, for example, in English, you don't ever have an vowel followed by a b. That never happens in English. Isn't a possible syllable rhyme. And so if you're listening to Hindi, and yet that is possible for Hindi, you could have you might be inclined to render it differently just because that sequence isn't.
So that's kind of the phone-to-phone mapping. I mean, that sounds like it would come into play in the phone-to-phone mapping, that the English listeners just can't hear certain phone sequences that exist in Hindi. Even if the individual phones do exist in English, the phone sequence might not.
Yeah, and similarly for letter sequence. I mean,
Yeah.
there's 2 levels, right? They have to hear the phone sequence,
Yeah.
but then they also have to produce a letter sequence.
Right.
Yeah, and a good example of what you're saying would be if you listen to an Indian American speaking Hindi versus a native Hindi speaker speaking Hindi, there'll be certain words which are mispronounced, even if,
Oh, that would be fun to cross-reference those data sets.
I have a 2-year-old that I'm trying to teach her Hindi, and she's already using a very different accent from,
Yeah.
so, from how I would say certain words, because the words she's hearing more frequently are English. So.
That would be great.
So I think the bottom line is to explore this decomposed model far more. Yeah. Okay, and the final step in this kind of sequence of doing this approximate decoding is what we call data filtering. So each individual transcript has some information, but it also contributes noise independently. And so some transcripts tend to be very noisy, and here noise is defined like I defined in the previous slide. So it turns out that the accuracy of the models can be improved if we are somehow able to filter these transcripts out. And so then the question is, how do we identify such transcripts a priori? So going back to our example of A and K, if we represent each of these transcripts as points in a metric space. So here, each of these points correspond to each of these transcripts. And the metric is just a Euclidean distance between the transcripts. So the distance between 1 and 2 is 4. The distance between 1 and 3 is 4 again. The distance between 4 and 5 is much shorter, and so is the distance between 2 and 5, and so on. So you find these edit distance between every pair of transcripts, and you finally have a structure which looks something like this. And here you can kind of pick out the outliers. So here 3 would be an outlier because it's much further off from the other transcripts. And 2, 5, and 4 are kind of agree more. But again, it's definitely debatable as to whether this is the only criterion by which you should. That's great feedback. So this is kind of how preliminary research experiments. Okay. So the experimental setup for the continuous speech task, again, we extracted Hindi speech from radio broadcasts. The vocabulary size now is much larger. It's 5 times larger than the isolated word tasks. And we used a trigram Hindi language model, which was trained on lots of Hindi text. And now the task is to recover these continuous Hindi speech utterances, and using only the mismatched transcripts. And so we had a total of 400 different word tokens in our evaluation set. And the setup was very similar, but now we have a larger number of tokens, and again, a fairly diverse language background. So here are the error rates without any data filtering. So unmerged corresponds to the best individual channel model. So there's no merging of transcripts. And so the error rate is 77%. It's pretty high. The merged transcript does significantly better. So these drops are actually very significant. So this is almost a 12% absolute drop in word error rate. Merging with this contextual weighting, again, further drops the error rate by another 6% or 6 to 7%. And combined refers to this decoding with a short list. So we assemble a short list of hypotheses which come from all of these various other models, and then we do exact decoding using just this restricted set of hypotheses. And that doesn't really improve over the best individual system. But now for you to build these ASR systems with data filtering, there are consistent word error rate improvements across the board. And in the final decoding of the shortlist, we see a very significant drop in word error rate. So it's almost like a 17% drop. And so the final word error rate is around 43%, which is a fairly respectable number given this is a large vocabulary task, and now we're looking at continuous speech and so all the associated.
So by filtering, you mean throwing away things that are great?
Yes, yes. So
you're strictly throwing away.
Right now, we did throw it away.
Oh,
yeah. But the contextual weighting is not throwing away anything. So it's
right,
being,
but the filtering
is throwing away. Yeah.
How did you set? How did you? Was there some threshold or
some
quota you were trying to meet?
We tuned a threshold on a held-out set and then used that for the evaluation set. So there was a threshold that just empirically tuned.
Okay.
So it turned. So the magic number for us turned out to be 6. So
in terms of edit distance?
In terms of the scores from this particular.
In terms of average edit
in
distance.
terms of average edit distance to every other transcript.
Out of 270?
No, like 15 different repetitions. So each segment was repeated 15 times.
Was transcribed 15
It was
times?
transcribed by 15 different crowd workers.
Okay.
And so each of those transcripts have a score.
Uh-huh.
And that score is essentially an average edit distance between that transcript and every other transcript.
So do you have a sense of how many transcripts you were discarding, and for each speech sample was some transcript discarded?
Yes. So the magic number was actually 6. So we had to discard 6.
Oh, 6 wasn't the edit distance. That was
no.
You had to discard 6 from 16.
6 worst ones if they were dropped.
So it was
actually
best kind of thing.
Yeah. So if you dropped the 6 was according to that metric, it significantly improved.
Okay.
And are you still using the channel model here for the
yes,
decoding?
Yeah, it's exactly the same.
Is that what combined means, or are you using it for all 4 columns?
So so there's a subtle difference. So the merged channel models were trained on these merged transcripts.
Okay.
But the what I call combined was just trained on individual invocations of the channel. But then you have a constrained hypothesis list, which you get from all of these merged models.
Then another explanation would, for the gain with the data filtering would be that the channel was mismatched, so that those 6 people were Chinese in the US, so had significantly different channel, and then you're using one channel which is for American students.
So the channel was like very heterogeneous. So it's
But it was one channel for
it was one
everyone.
channel. Yeah.
So
yeah.
that might be
Yeah,
another
absolutely.
reason.
Yeah, yeah.
Was it the same? Did you find that among the discarded, certain Turkers who just appeared frequently?
Oh, that's a
They
good point. I
the
did
Chinese.
trace
Someone
back to
with
the
a
IDs
recorded-
and blacklist them from.
Wasn't your personal.
Did you ask about their hearing, or did you impose any requirements on their listening conditions?
No, I didn't ask about the IDs. That might be
It's difficult to get them to respond if you ask them much.
Well,
So they should know.
sometimes people who want to do speech perception studies on using Mechanical Turk will put in catch questions where they
I
have,
see.
something is like at a very low signal to noise ratio, and
Mhm.
if they can hear that, then they pass.
Yeah, maybe that's worth including. So yeah, I think the motivation was to keep the task as short as possible, because the task in itself is kind of unnatural. Like they have to listen to this, and so people are probably not going to stick through it. But yeah, this might be like a very small kind of check to just make sure that we include only nominated participants. Yeah. But the other kind of checks that you typically use in speech perception experiments, so it's hard to come up with those kinds of checks here, because we are not trying to find whether someone knows a particular language. We're trying to find whether someone doesn't know a particular language.
Well, we do checks for things like, are they paying attention? So we have a trial that has just static noise on it, and then they're instructed if they hear that trial, they should answer in a particular way. And so every now and then you throw that trial out, and if they don't give the right answer, they haven't been paying attention, or something like that.
Right.
Or you just ask at the end for them to report on their listening environment, what kind of listening device were they using, so then at least you know, were they in a coffee shop or in a home office? And that might also could make a difference in what they hear. Like if they're listening through laptop speakers at the coffee shop, they're going to miss consonant sounds more than if they're listening to the same thing at home.
Right.
But that's just more noise.
I think my experience with these talks, it seems that people are more reluctant to kind of enter this kind of information. So even the language background, it wasn't the case that everyone who attempted it gave me that information, unless I made it kind of mandatory. But yeah, I could make this a mandatory question. Yeah.
How complicated was the channel? What was the intro? Is it a word to word, or phrase to phrase, or just syllable to syllable?
No, so it was Hindi phone, a phone sequence, to so it's basically English letters, a letter sequence, to Hindi words.
Hindi words.
Yeah.
Okay. So the size will be tens of thousands.
Yes.
Like the puzzle thing.
Yes. So the vocabulary size was close to 12,000. So yeah, and another point is we also computed the conditional entropy rate, and that was around less than 5 bits per word. So in the interest of time, I don't have additional slides about that, but I'll be happy to talk about it after the talk. Okay, so final remarks. So basically, this established the possibility of acquiring speech transcriptions using this concept of mismatched crowdsourcing. And this is very attractive for under-resourced languages, which are really hard to find native speakers. And future work is to experiment with a large set of languages, which Mark just talked about. So hopefully we'll have better answers to many of the questions that were asked today in a few months. And another interesting question for us is to quantify the impact of using these mismatched transcripts in building an actual ASR system. Finally, acknowledgements. I want to thank the Beckman Foundation for funding me, and collaborators Mark and Jennifer and Love have also given lots of feedback on this work. So thanks, I'm happy to take more questions.
Is this going to be a conference talk, or are you doing this talk?
So, yeah, so this was a conference talk in Jan, the first part, the isolated words. And the second part we just submitted, so to interspeech. Yeah.
I have a question.
Yes.
There is a mapping from the transcribed English letters to Hindi words, right? And the mapping is learned from a well-designed training data. So I'm just wondering, can we use a universal phoneme recognizer to be the encoder instead of the talker?
Yeah, absolutely. That's a great question and something that we have been exploring. So the only answer I have for you now is if you use like a mismatched ASR, so you use a universal phoneme, an English phoneme recognizer, and try to throw out phoneme sequences for Hindi.
Yeah,
so
can recover the Hindi words from the automatically transcribed English phonemes.
Yes. So if you use a kind of a standard GMM-based system, and we use an IPA kind of a rule-based merging of the phone sets, this outperforms that kind of a system using the mismatched crowdsourcing. But it's still not, so we're working on building better mismatched ASR systems. So a better universal representation would be to use like bottleneck features or...
What do you mean by mismatch? The degree of
so I just mean an ASR system trained on a different language, like a high resource language, and that is used to recognize the new target language.
The mismatch between the target and the source.
Yes. So the source is what the ASR system was trained on, and then you try to predict a phoneme sequence for speech segments in the new language. Isn't that what you? Maybe I misinterpreted.
Maybe I understand.
I think he was also suggesting the idea of a universal phone recognizer. So maybe a recognizer that recognizes all IPA symbols trained on a large number of languages.
Okay, right.
It could also be worth trying. I mean, that would be one way of improving the ASR. Another would be to use bottleneck features trained on a large number of languages.
Right. Yeah.
And better acoustic noise.
Okay. Yeah.
Because the utterance you tested is almost clean one, not noisy one. So I think a phoneme recognizer could be well performed on this to transcribe the clean utterance into phonemes. And then the phoneme to Hindi words mapping could be learned. Just as you learned from the human transcribed English letters to Hindi words. So I'm wondering what's a comparison if there are two systems. One is rely on a well-designed English phoneme recognizer, and another is relying on talkers. So is there any? So it's interesting to compare this.
So that comparison is definitely in the works. So to build a universal phoneme recognizer and then compare against these. So by clean, did you mean?
The speech is clean.
Yeah, but the speech was extracted from radio broadcast, so it's not entirely clean. So there are like artifacts of noise. But nevertheless, what you said is absolutely right. So we have to compare this against a universal phoneme recognizer.
Maybe you can ask different groups to provide different phoneme recognizers. So you can the transcription could have some diverse. Just one.
Yes. Yeah. That should definitely help.
Yeah. So far the crowdsourcers are beating the ASR, but my
But
other thing we can do is combine them. I think it may be. I mean, we have lots of experimenting to do.
Yeah, we this is the tip of the iceberg. Really.
Is there? I would have thought that
all the remaining parts could be the same.
I would have thought that if we had a universal phone recognizer, then we wouldn't even this at all. That's actually maybe the most difficult thing.
So
like without the knowledge of a language, without being embedded within any language,
I mean, if there was such a thing as a universal phone, right?
Well,
you just
a speech
said to
sound.
me, yeah.
Yeah, you just take all the speech sounds of all the languages. It's sort of like a machine version of a really good phonetician. I just I think that's a much harder.
So do universal phone recognizers exist?
IP to English phoneme,
Yeah.
just as you
Yeah.
use an English listener to transcribe.
Yeah,
IP.
there is
Not-
there is such a thing as a phone recognizer trained on many languages. We had one trained on 12. I think Tanya Schultz had one trained on 20. You run into this problem that a phone that has the same IPA symbol is actually produced quite differently depending on which language it was produced in. So there's no such thing as and you said that ah is robust, but it isn't. It sounds very different in Hindi from English.
No,
right?
if it's ah.
Okay.
No, I mean
Just
no, I don't think that's
Yeah, yeah. So this is a problem that sort of limits it. The other limitation that it runs. I mean, but despite these limitations, it's a good idea. It would probably help in this task. But the other limitation that we run into is that the distribution of phones has a very heavy tail. That you can choose almost any language on Earth, and it will have phonemes that don't exist in any of the other languages in your corpus.
Or maybe could be the phoneme recognizer could be restricted to only English phonemes.
Yeah, so that's
not the IPA is too broad a scope.
And this is where your idea of having multiple phone recognizers would probably help. If you have one that was trained on English and another that was trained on French and another that was trained on Chinese, that would probably be better than just having one that was trained on English.
Yes,
Yeah.
exactly.
Yeah.
And I guess that's somewhat equivalent to having a diverse crowd.
Yeah.
Yeah.
Yeah, exactly. Yeah.
Very cool.
And
Thanks
just
for the
out of,
question.
have you looked at some completely different approach? Seems like your filtering helped you a lot. So have you looked at other outlier removal techniques first,
No, this
followed
was just-
by, whatever you're doing?
Yeah, no, this was, I'm open to suggestions actually. This
So,
is
I
just
mean,
the first thing we tried.
I'm just trying to sell my work to you. So I've been
Okay.
looking at some work on robust PCA, but
Uh-huh.
not just that, but
Yeah.
in general, would there, as an initial filter to remove
Mhm.
outliers, and the way we study it, we
Right.
model outliers as sparse vectors or sparse matrices. But would that, as an initial filter followed by Xanath model, help potentially? Is that something?
Yeah, I mean, I'd like to talk to you after.
Sure.
this.
Right now, even I need to leave, but
Okay.
you can send me an email. Like, Mark knows me.
Yeah.
Okay.
All right, thank you very much.